Hello guys, welcome back to my YouTube channel. This is Pawan Kumar KN. I'm currently pursuing my computer science and cyber security course in Sri Venkateswara College of Engineering, Bangalore. Today we are here to discuss Epsilon transition. Introduction to Epsilon transitions. Epsilon transitions or E transitions are a concept in automata theory. They allow a finite automation to change states without consuming any input symbols. Their feature is significant in the design analysis of non-deterministic finite automata, shortly called as NFS. Definition of epsilon transitions. An epsilon transition is denoted by the Greek letter epsilon. It represents a transition that the automation can take without spreading any character from the input. This allows the automation to move to a new state spontaneously for strategic purposes. Epsilon transitions in NFS non-deterministic finite automata can have multiple possible transitions for a single input. Epsilon transitions add another layer of flexibility to the state transitions within NFA. They enable NFA to recognize certain patterns that deterministic finite automata cannot. Visual representation. Epsilon transitions are typically represented in state diagrams as dashed arrows. These arrows This visual representation helps in understanding the flow of states within the automation. In the context of automata theory, epsilon transitions are transitions in a non-deterministic finite automation where the automation can move from one state to another without consuming the input symbol. The key points of visual representation are graphical representation, purposes, and behavior. Epsilon closure. Epsilon closure is the set of states reachable from a given state using only epsilon transitions. It plays a crucial role in converting NFS with epsilon transitions into equivalent DFS. The epsilon closure helps in determining all possible states that can be activated without input. Conversion to DFA. To convert an NFA with epsilon transitions to a DFA, the epsilon closure method is used. This involves creating a new states in the DFA that correspond to the epsilon closures of the NFA states. The conversion ensures that the DFA can simulate the behavior of the NFA accurately. Applications of epsilon transitions. Epsilon transitions are used in various computational applications, including lexical analysis. They facilitate the implementation of regular expressions in programming languages. Epsilon transitions simplify the design of certain algorithms in pattern matching and parsing. Advantages of epsilon transitions. They enhance the expressiveness of NFS, allowing them to recognize a broader set of languages. Epsilon transitions can lead to simpler automata for certain patterns, reducing state complexity. They can also help in optimizing the automation by merging states through epsilon moves. Limitations of epsilon transitions. Despite their advantages, epsilon transitions can complicate the state transition diagram. They may introduce ambiguity in the automation, making it harder to analyze. Overuse of epsilon transitions can lead to inefficient automata requiring careful design. Conclusion. Epsilon transitions are a powerful tool in the realm of automata theory. They provide non-deterministic finite automata with enhanced capabilities. Understanding epsilon transitions is essential for students and professionals in computer science and linguistics.